I'm going to screen capture. I've got the other Year 12 class next. I'll screen capture both in case one goes pear-shaped. Here's where we got to, all right? And Malcolm, you startled me when you asked about the V squared on R. That's going to be the voltage drop, not the total voltage. So here's where we got to. In fact, I had to stop a little bit because the other lesson was screen captured, and here's where the other class got to. So the power is generated with a current of 12,500 amps. If you place that into your transmission lines and you tried to calculate the power loss, if you did I squared R using this value, well, that squared is going to be greater than the actual energy power being produced. So there's no way in hell all of the energy would get lost. Okay, that would be bad. So we know that if we step our voltage up, our current will reduce. We get it down to 500 amps, which is pretty nice. It's a relatively low current, hence the smiley face. Okay? Now, here's where we got to. There are two different ways that you can solve this question. One of them is looking at the voltage drop, knowing that our city is in series with the power lines. And the other is looking at energy considerations, looking at power here and power there, knowing that current is constant. So let's do both, and we'll confirm we should get the right answer. Now, you should have some room over the next page, okay? So I'm just going to go here and apologise that it's sort of over 2 pages. It should really be on 1 page. If we looked at the voltage drop, well, we already solved for the voltage drop up there, but I'm just going to rewrite it. Our voltage drop is going to be I secondary times the resistance of the wires, which we said was 500 amps by 3 ohms of resistance, gives us a 1500 volt drop. Okay? Then the voltage, we know that the secondary voltage is going to be the voltage drop plus the voltage at the city, because they are in series. So apologies, I'm just going to scroll back. We got to this part here. The city is over here. There would be a transformer here. Okay? And we would sort of, we'd transform our energy down here. So we want to know what the voltage at the city is as it gets to that transformer. So knowing that it's in series, we can rearrange for the voltage of the city. That's going to be our secondary minus what it isn't, and that was our 500 kilovolts minus our 1.5 kilovolts, and so we only get 498.5 kilovolts arriving at the city. Okay? So imagine your engineer, your electrician is at the transformer with his voltmeter. He's expecting it to read 5,000 volts. But unfortunately, he might be several kilometres or tens or hundreds of kilometres along a bit of wire, and that's taken some energy away, and it only reads 498.5. Now, at this point, we are lucky that the secondary current is constant, and it's 500 amps, which we calculated. So we could have an ammeter anywhere along. I could put my ammeter here, I could put my ammeter there, I could put my ammeter here. It's the same circuit. It's going to read 500 amps all the way through. This is one lump of wire all the way along. The current is constant. And so we can use that to figure out what the power supplied to the city is. So our power supplied to the city is going to be I secondary times the voltage of the city, P equals IV, 500 by 498.5 kilo. We get 249.25 times 10 to the 6 watts. 249.25 megawatts. Okay? So, conservation of energy there. We produced 250 megawatts, but only 249.25 megawatts got to the city. The amount that was lost must be what? 0.75 megawatts. That's the energy that wafts off into the air in the form of heat. Okay? Now, help me out here. Did I show you this demo towards the end of the last lesson? Yeah. Okay, cool. Now, this is a fun little relay volt. You can sort of flip the range. At the moment, we are transmitting 6 volts. There's 0.3 amps flowing through my circuit, 0.3 amps flowing through these wires, 0.3 amps flowing on this side, but we're only getting 0.2 volts across my city because I did not step my voltage up. So from this side of the transformer, 6 volts, to here, 0.2, I've got a 5.8 volt drop across my transmission lines, to the point where none of my globes are even glowing because they're only getting 0.2 volts. Kirchhoff's law still works. 0.3 amps on that side, 0.3 amps on this side. Okay? Now this is the fun little thing about this contact is, I'd like you again, I can't remember, all of yesterday was a blur, period 6. Let's just slide our, if I put my voltage here, alright, look, we're up at 6 volts. As I slide my voltmeter along, oops, losing contact. Now we're at 4.5, now we're at 4, slidey. Now we're at 2.5, and then finally, by the time we get over to here, we're down to under a volt. Okay? So, no good, no bueno, alright? Shall I keep going with... No, let's look at the second... I just decided to mix stuff up a little. Let's look at the second way that you could solve this. Rather than looking at voltage, which remember the voltage drop law is really conservation of energy. Let's look at power, which is also going to be looking at the conservation of energy. We have an equation that power loss is I squared times R. So let's look at the amount of energy that is lost in our circuit. 500 amps squared times 3 ohms gives 7.50 by 10 to the 5 watts. That is 0.75 megawatts, which is the number that I asked you to consider down here. Okay? So we did that at the end of the previous method. We figured out that 0.75 megawatts was lost, which is the same. Okay? All right. Let's now use our conservation that the power that the city receives is going to be the power at the supply minus that which was lost. So that's 250 megawatts minus 0.75 megawatts. That's 249.25 megawatts. Again, I could draw my little arrows. We're doing the same thing, just in different order, okay? And then lastly, since we know that IS is constant and it's 500 amps, I could then use my Ohm's law. My voltage at the city is going to be the power at the city divided by the current that runs through. So that's going to be my 249.25 megawatts over my 500. And what do you think we're going to get? That number that I'm trying to highlight there. Calculator spits out 498.5 kilovolts. Okay? So, again, there's no one correct method, which makes marking these kinds of questions tricky because half the class might do the voltage drop and then use the power equation, and then half the class might do the power and then figure out the voltage at the end. All right? But you can see it's all the same. You can figure out energy that's lost The voltage drop would manifest that energy being lost, which means the city would get the remainder. Yes?
When doing these questions, do we just choose one method and stick to that?
Well, I will. We've got on the next page, there is an example, and then there's a lovely example somewhere with the wind. There he is there. We will look. You've got two examples that we can have a look at in revision. All right.
So we shouldn't worry about the other methods, just focus on one method.
Focus on one method. I would probably say the left side method is the easiest, but it doesn't matter. Flip a coin, really. One student might prefer one to the other. All right, let's solve our problem of line loss. So let's bring in the dangerous element here. Here is my transformer, and I need to step this up. So I'm going to step this up probably by 60 to 1200, which is 6 to 120, which is a factor of 20. Yes? All right, so we'll step that up by a factor of 20. Now, I've got to make sure I don't damage things. We're going to step this up to, and I don't want to touch those cables because I will get a zap. So let's get to our proper scale. We'll turn him off. Now, I want my 1200 coils on this side, so it doesn't really matter with that. Reds or blacks.
So,
Yo.
how bad was that when you get?
Pretty bad. The current is low, all right. So you get a high voltage zap, but with a low current, but it would hurt. So here are my. Now this is not. The circuit's not on yet. No real humming. Oh, hang on, we have got a voltage. Oh, look, there is a potential difference on this side. Look, 100 and something. Quick maths. We said that we stepped it up by a factor of 20, so I've gone from 6 in the primary to 120 in the secondary. All right, so that's pretty much logic there. Let's now, if I gave 120 volts to these things, the power pack would probably short because then all of a sudden it's sending too much voltage through a small resistance. So let's step it back down over here. I've got my 120, so my 1200, okay? So we'll do the same ratio back down to get the same voltage, I would hope. And if everything's going well, we should get our lights to illuminate. Hey, look at that. Ooh, but look, our voltage has dropped a bit. Our voltage was over 120 when there was no load. And yet, when the little people in their cities are using the power, it dropped down. Why might that be? Go on.
Is that because those two are in series,
so the voltage drop only occurs when there is current running through our wires. If there is no current running through the wires, there's no voltage drop. Okay? So it's when the people are using the power that the voltage drop subtracts. So we were going to have 120, but now I've got to subtract an IR from that, or an I squared R if we look at power. Now I don't want to touch these, but let's just look at what the voltage drop was on, oh Jesus, let go. Over here, at the start, we should have no voltage drop. We're at 100, okay? Then if we slide it, and I'm not going to slide it while it's a live wire. So it was at 100, and then on this side, oh, hang on, 90, let's just say 95, maybe 96. Alright, so we got 100 at here, 96 at there, about a 4 volt drop. Okay? So I've got 1.2 amps here, I've got 1.1 amps here. There's a slight difference in amperage, unfortunately. 6 volts, 1 amp. We configure the power. 4 volts, 1 amp. Ooh, okay. I'm just rounding numbers here. 6 volts, 1 amp. 6 watts of power primary. The city is getting about 4.5 watts. So we're losing 1.5 watts in the transmission, which is a hell of a lot better than the first example where we lost all of it. Okay? Now, I want you to watch now. Let me just see if I've got a better scale. Hold on. Did we have a 100 scale? Yes, look, cool. Ring. All right. 100. No, 90. 96. Okay. Hang on. It's early morning and everyone's still asleep. And so the only things that are running are your fridge. Oh crap. On the scale. Oh well, that backfired. Let's go here. Alright. Now, I bring my voltmeter to my power supply and it reads a potential difference of 115 volts. Alright, it's early in the morning. And then we wake up. So maybe I turn on the telly, watch a bit of the Today Show, Good Morning Australia. The voltage dropped a little bit. Did you see that? It's now down to 110. Let's say it's middle of the day. Everyone's at work. Then everyone gets home. It's summer, 3 o'clock. You get home, first thing you do? Aircon, TVs, all right? Aircon, pool pump, washing machine, okay? So now, as everyone gets home in the afternoon, the voltage is dropping because the current is increasing through your transmission lines, okay? With more demand, there must be more current flowing through. With a greater current in our high voltage power lines, we get a greater voltage drop. And that's one thing I want you to appreciate, is that the voltage across your live and neutral point is around about 240. It's never going to be equal to 240. One day it might be 240.3. The next day it might be 239.9. It ebbs and flows. These devices that I was pointing to yesterday, they can handle a range of about 230 to 240. Beyond that range, they won't operate. Okay? So, this is why there is an issue when we have heat waves, or in times of peak electrical demand. If everyone's getting home, turning on the aircon, turning on the dishwasher, turning on the TV, the pool pump, everything's going, boom, 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 more current through our wires, the voltage that actually gets to your city and to these power points starts to drop. And if it gets below around 235 volts, appliances stop working. So Synergy monitor which suburbs, which regions are using the most amount of electricity, and occasionally in the middle of summer heat waves, if we're running the risk of too many people consuming electricity, they will just pull the pin on a couple of suburbs. And so you can sometimes get home, and the city of Stirling had a rolling blackout where 20,000 homes were without power for a couple of hours. And it was basically just that there was too much demand on the grid, and Synergy just had to pull the pin so that current reduced, so that the voltage drop reduced, so that everyone else was able to get the required voltage. So that's where you get rolling blackouts. Yes?
So you have stepped down voltage from the power lines.
Yeah, by the same factor. So we stepped it up by a factor of 20, so 6 to 120, and then we stepped it down by a factor of 20 to bring it back down to 6 volts. Okay? The term, when the voltage drops below the required limit, I believe it is called a brownout, where, not a blackout is where the grid, tree falls on a power line, circuit's broken, but if the voltage drops below an acceptable limit, we've got a brownout. Then to prevent brownouts, Synergy can sometimes do rolling blackouts, and that's when you get housewives on the news that are angry because, I was without air conditioning for 2 hours. Yeah? And again, they don't do it for too long, or else everyone's food is going to get wasted in the fridge and freezers, and obviously hospitals and stuff have backup power supplies so that people don't perish. Okay, so could you please? I'd like you to do everything that I did on that previous page. Let's just add. Oh, come on, Justin. Let's give a resistance of 5 ohms in our transmission lines. I would like you to do a number of things. So obviously A and B and C, but then also let's find the voltage drop. Let's find the power loss. Let's find the power that the city receives, and hence find the voltage that the city receives. Okay? Please. So, obviously, since I've put a resistance, we know that the city is not going to receive 500,000 volts. It's going to drop slightly because some energy has been stolen along the power lines due to heat. Okay? So could you do that for me? And again, we're looking at a massive question here with about 15 marks worth of stuff. So again, 15 minutes of your time, please. And I don't know where you're going to answer D, E, F, and G. Probably somewhere on the next page. There's room. Huh? Yeah, but we're kicking it old school here with pen and paper. And I would just say, throw everything down. Shall we assume an ideal?
Yeah.
Sure, why not? All right, so what can we do? We can pre-fill power is 100 megawatts. Voltage is 100 kilovolts. Your secondary coil is 10,000. Voltage over here is 500 kilovolts. All right. NP on NS equals VP on VS. Please do. Yes, this was done poorly by me. Now, I've just added this resistance, and maybe I didn't step it up enough. Maybe my resistance was too much. We'll just find the consequences. Maybe we lose lots of power because my resistance was too high, but we will find out. 500, 10 to the 3. And I've only stepped it up by a factor of 5. So that's 2,000 windings. Are we correct at 2,000? Cool. Then the current that flows in the secondary coil.
So
100,000 on...
resistance is always 5 ohms?
I just made it up. You'll find in questions there are around about 1 to 10 ohms. So those power lines are going to be massive, big, chunky bits of copper. All right, large diameter to have the lowest possible resistance. Do we get 1,000 on 5 equals 200 amps? Oh wait, I've got the answer here. Yes, we do, Mr. Murray.
Marcus?
Yes, what?
Can you pass a dash sheet, please? Thank you.
Oh wait, we didn't get primary, so there we go.
I've got one.
All right, you can answer part C in your own time. Let's do part D. $200 times 5 is 1,000 volts. Therefore, power loss.
Can't you just do these IR for voltage drop?
That's what I did. Oh, Mr. Rahal. So again, you might wish to do both methods to confirm that you got the right answer. You might want to do the voltage drop order first to get your answers, then you might want to do the power next to get your answers. 200 squared, is that 40,000 times 5? I've got a calculator here. I answer my own question. 200,000. Okay, so these values are somewhat significant. 99.8 megawatts gets to the city. And so our voltage drop would be less. 9.8 divided by 2 gives us 499. Oh, duh. Of course it's 499 because the voltage drop was 1,000. So it's 500 less 1,000. Cool? Mr. Malcolm Wang, we could also then confirm, does V squared on R also give 200,000 watts? Good. If that didn't work, I would be very, very worried. So there is now 3 methods to figure out the energy loss. V squared on R, I squared R, V equals IR. We have options here. Okay? And then lastly, our good old explanation. Well, when voltage is stepped up.
What was F?
99.8 megawatts. So 200,000 watts was lost.
No, I just meant the question.
The power that the city receives.
Yeah, and then the voltage.
And remember that would be the primary voltage at the city's transformer. Yeah?
Yes.
So you've got 2 transformers at each end. So the first transformer would be the secondary there, and then the first transformer would be the primary at the city. So it's a bit tricky, and that's why I tend not to worry too much about the city. You could do a whole other set of transformer questions at the city's transformer.
Yeah.
When you find the power loss, can we just find the power of the city and take away the...
Yes? Yep. Well, you'd find the voltage at the city,
Yeah.
and then P equals IV. You would find that P is 200,000 watts less. Okay. Now, you all have options. I have a transformer validation that you could do. Or, as I said, there was one little question. So that's pretty much me stop talking. We're done. We're finished. You might wish to have a look at questions 23 to 26 in the revision, or you can look at this validation question. I'm not going to mark it. It's not test conditions. I'll give the solutions out. In the last 10 minutes, I'm going to hand out your investigation, and we'll have a chit chat about things. Yes,
Could you like scroll after you hand out? Can you scroll back up to like Z? I haven't fully copied it down.
Yeah. Yeah.
Take mine, doesn't matter. I
What questions? E, F, G.
It's fine. So it's fine. I've given it mine.
Oh, there we go. Look at that. Teamwork makes the dream work. Is there two there, Ben? Can we just confirm that?
There are indeed two here.
Brilliant. So guys, just give me 10 minutes of working on a transmission question for me, please.
Is it 99.9?
99.8.
That's what I got. I don't know. 1, 2, 3, 4, 5, 6.
Yes, Mr. Malcolm Wayne.
2 times 10 to the 5.
Because we're on the primary side. Yeah, we have not yet gone over to the secondary of the city. So this ammeter will just in that question, that voltage is across the primary, the first transformer, the first coil in the next transformer. So if you see on this diagram here, we were here, when you said V city, we're actually looking on this side. This side, primary. So we were looking here, which is actually now V primary of the next transformer. Okay, so over here, this, we would have said V secondary was 500 kV, and then here V primary was what, 499? No, just 499 kV. So that would be the example, Malcolm, was me taking the voltmeter and sliding it along. If I started here, it would read 500,000 volts. As I slide it along, here it would read 499. Before the second transformer. Okay? Then the city could step it down. If they step it down, then we can do the whole V on V, then on N again. Okay? All right. So we'll stop the recording.